So,
Yeah.
Today, what I'll do is I'll introduce PTC heaters. Some of you may be familiar, and then the expected performance of those heaters. And then we'll go into the design principles that we use in order to help our customers design these circuits. And then finally, I'll share with you a case study where we worked with our partner Boyd in improving a customer's design. So next, please. So what are PTC heaters? PTC stands for positive temperature coefficient of resistance. For typical metal heaters, as your gold, silver conductor heaters, these are linear heaters. So they increase resistance with the increasing temperature, as we see here on our graph on the right. It looks like this is on a timer, so I'm going to make sure it might go a little quick.
No, I'm moving them along. I'm moving them
Oh,
along.
you're moving it along? Okay,
Yeah,
thank you so much. So perfect. So as you can see on the bottom right, linear heaters has a linear response. Our PTC polymer heaters are designed to have a near exponential response. So if you move it forward one more, you'll be able to see an example of the green line here. So as the difference, right, is that at a specific temperature, we get a drastic increase in temperature. And if you increase it one more, the benefit of this is it gives it this self-regulating temperature behavior, which just allows us to design smart heater applications. Next slide, please. All right, so if you go forward about two more, the characteristics that we're looking for PTC heaters, one is the switching temperature range. This range corresponds to a specific resistance magnification factor, the R factor. So again, this is kind of your resistance normalized by your resistance at room temperature. For our heaters, we typically recommend a range of 2x to 10x, depending on the design and the customer needs. The advantages of having this near exponential response is, again, we get that self-limiting temperature control. So we're able to dial in the temperature without the need for external sensors or controllers. We have fast heating time to operating temperature because we're not worried about temperature overshoot. And then also we have 10x or greater resistance shift at the target temperatures. Please go ahead one more. The applications involve heaters, sensors, as well as overcurrent protection. Next slide, please. So to test these materials, we use a voltage sweep test. So on the left here, you can see a diagram of our typical setup. Below, we have a heater that we printed in-house. Our silver conductor is our Priolex AG800, and we printed PTC 4980 heater, PTC paste on top. This specific circuit is designed to go between 20 and 50 volts. So we apply a linearly increasing voltage across the sample, and we measure the results. And we can actually calculate while we're running the results, since we're measuring both current and voltage, the resistance. So the blue line on the left is our temperature over voltage, and on the right side, that is our R factor as a function of voltage. And if you click ahead one more, we are looking for a target R factor of between 2 to 10. So that's this range here. And we click again once more. And we can see that goes to this corresponding temperature of 65 degrees to 90 degrees. So this is the recommended operating temperature as we reach that plateau area. So this is how we typically design our heaters. So we look at kind of the dimensions and the spacing, and then figure out how the performance is going to be. Next slide, please. So the first step would be to define the application, the target temperature, area to be heated, driving voltage, desired heating power, as well as a thermal load. And then step two, you could work with us to work on your heater design. So on the right, you can see that we have our conductor bus bars and our PTC resistor cells. This is a very typical type of design that we use, but the sizing is really what matters. So we have both high and low versions of our PTC inks, where we're able to dial in the sheet resistance based on your application. And we also design the patterns in terms of not only paste properties, but the physical dimensions. So if you click forward again, we look at the resistance, which obviously is a function of the resistivity of the paste itself and the area and the thickness. This is one input for us. And if we continue looking at other inputs, go ahead and click ahead. The spacing of the PTC resistor cells along with the width